Hello students, today we are going to learn through this session the application part of electric charges and fields. To know about this application part, the numerical problems clearly, you must one time revise the theoretical part of all the before sessions, right? Problem 1, 2-point charges 3 μc and minus 3 μc are located 20 cm apart in vacuum. The questions are A. Calculate the electric field at the midpoint O of the line AB joining the two charges. And the question B is, what is the force experienced by a negative test charge of magnitude 1.5 into 10 power minus 9 coulomb placed at this point? See, we have said about the 2-point charges 3 μc and minus 3 μc, which is separated at a distance of 20 centimeter. Right, they have given. So first you have to calculate the electric field at the midpoint O. Here, the midpoint O, we have to calculate. The line AB, we have taken and given the name for that QA charge is A, and I have given the name for the minus Q, that means the QB minus 3 μc, for that B we have given the name, right? Now the line AB joining the two charges. First we have to write the given, and what is the line joining point and all, we can check it. So QA, the value QA, which is equal to, they have given 3 μc. So, which is equal to, we can write 3 into 10 power minus 6 coulomb. Okay, that you have to write coulomb. So, here they have given AB line joining. So, AB line joining, you have to take it for that positive charge, because the charge which is at A. So, that you can take 20 centimeter, or we can write 0.2 meter, right? And here for the QB value, we have taken minus 3 μc. So, which is equal to minus of 3 into 10 power minus 6 coulomb. Here you have to take from that, for that B, from the line adjoining OB you have to take. Or you can take OA, or you can take OB, which is equal to, you can take the half, which means what it will come. This is 2A. So, the value which you can take 2A. So, you have to take only that A value is 10 centimeter. So, that is equal to 0.1 meter. Got it? Now, here you can recollect one point, theoretical part. You have to recollect the theoretical part. You can pause this video and you can check the previous video of the theory part which we have taken about 2-point charges which is located at a distance, which means what, children? Yes, this and all you have to check previous video. Then you can get the clear idea of theory. Always the numerical part is the application oriented of knowledge. So if you check the theoretical part clearly and work it out in a paper, easily you can approach the problems. Yes, hope I believed that you may check the previous video. So the theoretical part, I will recall it again. So we know that the 2-point charges which is separated at the distance, which means it's a dipole. This is the application of dipole. The application of dipole we have taken in the line joining, it is axial, on the axis, the point which is on the axis. So that this is for the axial we have taken. So take the formula E, which is equal to EA vector plus EB vector. That means the electric field which is at point A, the charge, point charge at A, and the electric field at point charge B. As we know very well, the electric field formula is what? E, which is equal to E vector, which is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So again and again I am telling children, these are all the things of the application part. You must check and practice the theoretical part. It is very easy to approach the numerical. Now we can see and apply the value of 1 by 4 pi epsilon naught, that is 9 into 10 power 9, and the E1 and E2 value, that is 3 into 10 power minus 6 whole divided by 0.1 the whole square. So, R square value, Q1 value, plus you have to add that EB value, the electric field at B, that is also 3 into 10 power minus 6 whole divided by 0.1 whole square. Got it? So this is along along OB. We have taken along OB and OA. That is only they asked. We explained that also. And finally, we will get the E0 value 5.4 into 10 power 6 Newton per Coulomb. That is for along OB. When you simplify this and by applying that mathematical formula, you will get the value E0 which is equal to 5.4 into 10 power 6 Newton per Coulomb, which is for the electric field. So the second part of the question is, what is the force experienced by a negative test charge? The magnitude 1.5 into 10 power minus 9 Coulomb, which is placed at this point. So we have taken the Q0 which is equal to minus 1.5 into 10 power minus 9 Coulomb. So at the midpoint. The question is what? The force which is experienced by the negative charge. So you have to know about the electrostatic field which is equal to force per unit charge. That formula. So electrostatic field E vector or E0 vector which is equal to F vector by Q. We need F. So F which is equal to E0 into Q. So this is the formula we remodulate and we can apply the values, right? So we can apply the values of F0 which is equal to 1.5 into 10 power minus 9 into 5.4 into 10 power 6. So by simplify this, you will get 8.1 into 10 power minus 3 Newton. So this is the force which is experienced by the negative charge, the magnitude 1.5 into 10 power minus 9 Coulomb placed at this point. Yes. Problem 2. The electrostatic force on a small sphere of charge 0.4 mu Coulomb due to another small sphere of charge minus 0.8 mu Coulomb in arrows 0.2 Newton. The questions are, what is the distance between the two spheres and what is the force on the second sphere due to the first one? First we can write what are all they have given. Charge on first small sphere which is equal to Q1, that is equal to they have given 0.4 mu c. So mu z microcoulomb we have to take it 10 power minus 6 Coulomb, right? So Q2 that value charge on the second small sphere Q2 which is equal to minus 0.8 mu z, that is equal to minus 0.8 into 10 power minus 6 Coulomb. And about the electrostatic force on the first sphere due to the second, they have given the force which is equal to 0.2 Newton. So we have to calculate the electrostatic force between the spheres. We know that F which is equal to Q1 Q2 by R square. That K into Q1 Q2 by R square. The K value only we know that is equal to 1 by 4 pi epsilon naught, right? Here we need, the question is, what is the distance between the two spheres? From the base formula, we can modify it, right? We need R square which is equal to Q1 Q2 by 4 pi epsilon naught into F. By applying all the values, we will get, so that is equal to Q1 value is what? 0.4 into 10 power minus 6 into Q2 value 0.8 into 10 power minus 6 into 9 into 10 power 9 is 1 by 4 pi epsilon naught value which is equal to 9 into 10 power 9, right? So F value we got it, that is 0.2. So we are going to simplify this value. So as we know that the 0.4 we can take and 0.8 this value and 9, if you have simplified that, you will get then 2.88 into 10 power minus 6 and 10 power minus 6. This two value you have to calculate. 10 power minus 6 and 10 power minus 6 you have taken means you will get 10 power minus 12 and you can take that plus 9, the whole divided by 0.2. So we will get the r square value by simplified this one, r square which is equal to that 144 into 10 power minus 4 you will get it. So r value we need, so root of 144 into 10 power minus 4. So we get r which is equal to 0.12. So r which is equal to 12 centimeter. Okay, 0.12 meters, so 12 centimeter you will get the distance. So the distance between the two spheres r which is equal to 12 centimeter. So the second part, what is the force on the second sphere due to the first one? Here, both the sphere attract each other with the same force, right? So that the force on the second sphere also we can take the first sphere. What is the first sphere? We got the electrostatic force on the first sphere due to the second force is what? F, which is equal to 0.2 Newton. So the both the same force, it attract each other, so that we'll take the force on the second sphere due to the first one is also 0.2 Newton. Yes, third problem. An electric dipole with dipole moment they have given 4 into 10 power minus 9 coulomb meter is aligned at 30 degree with the direction of the uniform electric field of magnitude 5 into 10 power 4 Newton per coulomb. Calculate the magnitude of the torque which is acting on the dipole. So we need to know about the formula for the torque. So you must calculate the magnitude of the torque which is acting on the dipole. What is the formula for the torque? So torque tau which is equal to, we can write tau which is equal to PE sin theta. So this is the formula, and we can write what are all that they have given. So they have given as electric dipole moment, right? P which is equal to 4 into 10 power minus 9 coulomb meter, and theta which is aligned 30 degree they have given. So theta which is equal to 30 degree, and the E which is the electric field of the magnitude E which is equal to 5 into 10 power 4 Newton per coulomb. So these are all the things they have given. So with the help of the given we can apply the values and we'll get tau value directly. So we can apply, no need of any modification in the formula. So P value is 4 into 10 power minus 9. Into that we can write the value for 5 into 10 power 4 which is for E value into sine 30 degree. So sine 30 degree will get half 0.5, right? So 0.5 you can apply. Then tau which is equal to, you can get it 10, that is 5, okay, 100 you will get it into 10 power minus 9 plus 4. So we'll get it tau which is equal to 10 power minus 4 Newton coulomb. So you will get the value for the tau which is equal to 10 power minus 4 Newton coulomb. So problem 4, consider a uniform electric field E vector which is equal to 3 into 10 power 3 I cap Newton per coulomb. The question is, what is the flux of this field through a square of 10 centimeter on a side whose plane is parallel to the YZ plane? And what is the flux through the same square if the normal to its plane makes a 60 degree angle with the x-axis? First we will write given. So they have written, they have given is E vector, that is electric field which is equal to what? 3 into 10 power 3 I cap Newton per coulomb. And they have given, yes, the surface square of, what is the flux of this field? The flux which is there in the sphere, which is, the surface is 10 centimeter. Okay, so S which is equal to, we can take 0.10 whole square I cap meter square. So surface, so that we have squared it, area, which is equal to, we can write 30 into, so this value we can keep it like this way only. Then the question A, which is nothing but What is that? Phi E, the flux value, electric flux, which is equal to, what is the formula? E vector dot S vector. So this is the formula for that, right? So applying the value, E vector value, which is equal to 3 into 10 power 3 into, we have to write 0.1 I vector dot 0.1 I vector. We will get the value of, so I vector dot I vector, which is equal to 1. Okay, the dot product of I dot I, which is equal to 1 by applying that mathematical, that vector formula. So you will get here 30 and Newton meter square Coulomb power minus 1. So this is the value for the A part, phi E, which is equal to 30 Newton meter square Coulomb power minus 1. So the B part is, what is the flux through the same square if the normal to its plane makes a 60-degree angle with the x-axis. So that for that, the B part we can write the phi E formula, which is equal to ES cos 60 degree. So for that, we will apply the values 3 into 10 power 3 into 10 power minus 2 into cos 61 by 2, right? So we will get the value is 15 Newton meter square Coulomb power minus 1. So this is the value for, if suppose it normal with the angle of 60 degree means phi E, which is equal to 15 Newton meter square Coulomb power minus 1. Problem 5. 3 point charges of plus 2 mu coulomb, minus 3 mu coulomb and minus 3 mu coulomb are kept at the vertices of A, B, C respectively of an equilateral triangle of side 20 centimeter as shown in the diagram. And what should be the sign and the magnitude of the charges, a charge to be placed at the midpoint of sides BC, so that the charge at A remains in equilibrium? By reading the question and seeing the diagram, you may understand this is the application part of the theoretical, of which one you can recollect it, you recall. By pause this video and you can recall, and you have to see the previous theoretical part of the 15th chapter, the previous videos, you will get the idea of it, right? So I'll tell that this is the dipole, application of the dipole at the equatorial point. Let us resolve the sum. So the solution we can see, so from explaining the diagram itself we can got it. So we said the question is what? The 3 point charges plus 2 mu c minus 3 mu c and minus 3 mu c, which is separated at a distance of 20 centimeter, and this is at the vertices, respectively this is the equilateral triangle, right? So it is apart the 20 centimeter sides we got it. So the question is, what should be the sign and the magnitude of the charge to be, if suppose, placed at the midpoint of the sides BC? So the charge A remains at the equilibrium condition, equilibrium position, right? Now the given value, the net electric field at A due to the charges at B and C, it is EA, which is equal to 2 EAC sine 60 degree, because as per the theory of equatorial, the cos function or cosine component will get cancelled out. So we'll only go with the sine component. So we got from the question, we got the clue, only the clue we got it. Net electric field at A due to the charges at B and C is what? EA, which is equal to 2 into EAC sine 60 degree. So we'll get the value for that by applying EAC and sine value. EA, which is equal to 2 into 3 into 10 power minus 6 is 1 Q value, whole divided by R square. So 20 into 10 power minus 2 into sine 60 degree, which is root 3 by 2. So by simplifying this value, you will get EA, which is equal to 1.5 root 3 into 10 power minus 5 Newton per Coulomb. So we need to know about the sign and the magnitude value of the midpoint, the charge which is placed at the midpoint M, so that we need to know about AM value. So AM, which is equal to, by applying Pythagoras theorem, root of 20 square minus 10 square. We'll simplify this value. We will get the AM value is what? 10 root 3 centimeter. Now we need to know, we have taken the charge at M. Here we don't know that the sign and the magnitude, so that we have given the value as Q. We have taken as Q. So let charge at M, which is Q. So by applying in force F AM, which is equal to what is the formula? Yes, K Q1 Q2 by R square. So that we got it 1 by 4 pi epsilon naught. 2 into 10 power minus 6, 1 Q value, another Q we have taken as a Q. So Q whole divided by 300. So by applying 1 by 4 pi epsilon naught value is what? 9 into 10 power 9. So 1 Q value is 2 into 10 power minus 6 into Q whole divided by 300. This we have taken as a first equation. And we know that very well, the F which is equal to QA into EA, that is nothing but the electrostatic field, which is equal to force per unit charge. From that we got the force which is equal to QA into EA, right? Here FAM we have to take it, which is equal to, then from the above explanation part, 2 into 10 power minus 6 into the E value is what we got it? Yes, 1.5 root 3 into 10 power minus 5. This we can take it as second equation. So from the equation 1 and 2, we will get Q value will apply. Q which is equal to 2 into 10 power minus 6, 1.5 into root 3 into 10 power minus 5 into 3 into 10 power 2 whole divided by the 4 pi epsilon naught value, 9 into 10 power 9 into 2 into 10 power minus 6. So from the equation 1 and 2, you have to calculate and apply this, right? Q value. By rearranging this base formula, you will get it. So that we can simplify. So 2, this both will get cancelled out. And you will get here also will get cancelled out. Then the remaining part, 1.5 root 3 whole divided by this 3. Here you will get is minus 5. So 10 power minus 5 plus 2 whole divided by 10 power 9. You will get then 10 power minus 3 minus 9. So you'll get 10 power minus 12. Okay. So, so this is the simplification process that you can do it. You will get finally then root 3 by 2, that picocoulomb. And also from this point you can understand the charge Q is a positive charge. Okay. Right, children? So the value of Q which is equal to root 3 by 2 picocoulomb. Problem 6. Two large parallel thin metallic plates are placed close to each other. So the plates have surface charge densities of opposite sign and magnitude 20 into 10 power minus 12 coulomb per meter square. Now we are going to calculate the electric field intensity of outer region of the plates and the inner region of the plates. For this also, children, you have to recollect the theory part of the application of Gauss law. So this is the application of Gauss law, the parallel plates. For the plates you have to take it. Here the outer region and the inner region both we are going to calculate it. First we can see that the electric field due to the positively charged plate, which is given by E1 which is equal to sigma 1 whole divided by 2 epsilon naught. We have taken sigma 1 here. For the electric field due to the negatively charged plate is given by E2 which is equal to sigma 2 whole divided by 2 epsilon naught. For we have taken sigma 1 and sigma 2 as sigma. The two plates we have taken as sigma. Now we are going to calculate what is the electric field intensity outer region and the inner region. Right? Yes. Now for the first question, the electric field intensity in the outer region. So we have taken the net electric field in the outer region is, as per the theory, E which is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0. It will get cancelled out in the outer region, so that the electric field intensity is always in the outer region is 0, right? Now, the net electric field in the inner region, you have to add both the values. So that E, which is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught, we will get sigma by epsilon naught is the final theoretical proof. We got it from that. So by applying the values of sigma and epsilon naught, we will get 2.26 Newton per Coulomb. See, the value of sigma 20 into 10 power minus 12 Coulomb meter power minus 2 whole divided by this epsilon naught value is a standard permittivity value, that is the 8.85 into 10 power minus 12 Coulomb square Newton power minus 1 meter power minus 2. So simplified this, we got 2.26 Newton per Coulomb. This is the field intensity in the inner region of the two plates, right? Yes, students. So far we have learnt the application part of the theoretical electric charges and field, the various numerical problem we derived and achieved. That is, for example, dipole at axial in the equatorial part, and we have learnt about the tau, the torque, and we have learnt electric field intensity, like various problems we approached. So the theoretical part of the application oriented numericals we have learned through this session. Hope you will understood and you can achieve more and more problems which we have given, right? Thank you, students.